Hello everyone, I'm Chinedu Ifeanyi Chukwuma, and today I'll be presenting a project titled Design and Real-Time Simulation of a Solar Energy System for Charging Electric Vehicles. The focus of this paper will be on developing nations using Nigeria as a case study. Here's a brief introduction of this work. According to the US Department of Energy, the transportation sector continues to be a leading contributor to greenhouse gas emissions. And to address these growing global emissions, the International Energy Agency introduced the Net Zero Roadmap in 2021, which details critical measures such as accelerating the adoption of electrification and biofuels, which are critical for reducing carbon emissions in the road sector. And so, if you look at the transportation sector, it contributed 8.3 gigatons of CO2 emissions in 2018. And so, it has brought about this global drive to reduce GHG emissions. And this has led to electrification of the transport sector becoming an important driver of decarbonization. Various policies have been implemented in various nations to encourage the adoption of electric vehicles. And for our focus being on Nigeria, the Nigerian government presented at COP26 their plan for full transition to EV. And this was to achieve carbon neutrality by 2060. But globally, we see significant investments in research and production of EVs, charging infrastructure, which has led to massive EV registration globally, especially in Europe, Canada, and the US. But we don't see this drive in developing nations. And this is due to critical infrastructure not being present, such as maybe epileptic grid in developing nations. And so this is what we try to address in our work. So the objectives of this work is to design and simulate a solar system to charge an electric vehicle in a developing nation. We are using Nigeria as a case study for our work, and we'll be using some tools, Homa Pro and MATLAB Simulink student versions for our analysis. And we aim to understand the system performance by varying the temperature and irradiation for our chosen location to reflect dynamic environmental conditions. And also, another objective is to advance emission-free transportation in developing nations. Here's a general overview of this work. We can see the block diagram. We have the PV array, the charge controller, the standby battery bank, a DC-DC converter, and then the electric vehicle to be charged. And so the PV array provides the source of power for the system. We know how photons hit the PV cells, dislodge electrons, and produce a potential difference. And so the charge controller here, it's just a DC-DC converter. It serves as a link between the battery and the PV array. We also have the battery bank, which is due to the intermittent nature of the sun. It serves as an energy storage where excess energy produced is stored. And then we have another DC-DC converter that is necessary to transfer power to the electric vehicle charging infrastructure. So that's the electric vehicle there. And here's our block diagram on Homa. We have our PV, which is connected to a DC bus. And then we have our EV, that represents the EV charging infrastructure, also connected to our DC bus. But here we had to model the load. and we got the distance covered in a year from literatures we found, and then the all electric range for the vehicle we use the Hyundai, the Hyundai Kona, and so the range from there we are able to get our daily energy consumption. We know the all electric range for Hyundai Kona is 258 miles. From there, we found our daily amp-hour requirement and the battery amp-hour required for this system, which from the calculation it guided us in setting up our system on Homer. And then we ran our simulation to get an optimized solution here, which guided us in the next phase of our work, where we modeled on MATLAB Simulink. Here we present our Simulink system setup. You can see our PV array, then with the buck converter, and then our boost converter connected to our EV. So the parameters here, they are presented on the table above, that's for the buck converter, and the table below for the boost converter. And we got our parameters from, like, for example, the output current we calculated from the rated power divided by V out. We got our current ripple for the buck converter, which is 10% of our output current. And then the voltage ripple, also 10% of our V out. We calculated our inductance, we calculated the capacitance values, which we use in our simulation. And then we present the values. You can see them on the table above. And also for the boost converter, we did a similar thing. We calculated for the input current, which is the rated power divided by V in. We calculated for the current ripple. We calculated also for our output current, and then we got our inductance and our capacitance values. From these parameters, we're able to calculate our duty cycle, which we use for our simulation, and then we ran our simulation. Here we present the voltage and current, which we monitored from our PV output, that's to charge the lead-acid battery. So we analyze the dynamic response of the system by monitoring the voltage and currents from the PV that is required to charge the lead-acid battery, and ensured that the system worked efficiently. The buck converter stepped down the output voltage from the PV to 300 volts, and this was used to charge the lead-acid battery. Then the boost converter stepped up the voltage from 300 volts to 430 volts, which is needed at the terminals or the charging, the EV charging infrastructure to charge the EV's lithium battery. So, and we know that when we are able to charge the lead-acid battery, then the boost converter converts the voltages, makes it appropriate for charging the EV's battery. And so we can see the state of charge. It increases in both the lead-acid battery and the lithium battery for the EV. Also on top, we can see the voltage levels, the 300 volts at the lead-acid battery, and then we have 430 volts for charging the EV. And also we can see that the current is stable, which makes all these our results here suitable for our system. Here we present the results from our simulation when we varied the temperature from 25 to 40 degrees. In doing this, we try to simulate real-time environmental conditions on our system, and we can see that the PI controller was able to give us our desired outcome as the state of charge increases smoothly, as can be seen on the plot here. And also our control system adjusted the duty cycle to compensate for environmental variations. As you can see, the voltage remained stable. Also the current was stable irrespective of the varying temperature. And so we're able to get our desired outcome, which is to ensure that we are able to charge the battery of our EV in a chosen location. In conclusion, from our simulation, we have designed a solar energy system for charging electric vehicles in developing nations, and we use Nigeria as a case study. And the results from the steady state analysis we did shows that the abundant solar resources in Nigeria is sufficiently able to charge an electric vehicle. And then the dynamic simulation results also show that the closed loop control system for our solar electric vehicle charging system can ensure that the charging voltage and the current of the system is stable, irrespective of the fluctuating environmental conditions. So we present this standalone solar system, which could be used for residential premises, and we hope it will encourage the adoption of electric vehicles in developing nations. And also, it can also support long distance transportation if this system is scaled up at intervals along the long transport network. We believe it will greatly reduce emissions, which is one of the drive globally. Thank you very much for listening.